Taylor and Maclaurin series. Here we want to be able to use the information from the previous sections to build the actual representation of functions either based on Taylor or Maclaurin. Here we get the series, not a polynomial going out to n factors or to the nth derivative, but we want to be able to say that this function or this term is equal to based on the so-called Taylor or Maclaurin series. So the form of a convergent power series is of this form. The definition of Taylor and Maclaurin series: if f is a function that has derivatives of all orders at x equal to c, then the series here is said to represent the Taylor series for f of x centered at c. If c is equal to 0, then the series, obviously, you recall, is called the Maclaurin series. What I want to do is to be able to build some basic series based on Taylor and Maclaurin. Right? The basic representation of the following functions using either Taylor or Maclaurin power series. First, let's start with f of x equal to e to the x, here where c is centered at 0. We know that f of 0 is e to the 0, that's 1. F prime of x is e to the x. F double prime of x, e to the x, and so on. The nth derivative evaluated at x is e to the x. So f prime of 0 is 1. F double prime at 0 is 1, and so on. The nth derivative at 0 is still equal to 1. So using here Taylor, particularly Taylor at c equals 0, the Maclaurin, we can write here the expansion for e to the x. And so this is f of 0 plus f prime of 0 times x plus f double prime at 0 times x squared all over 2 factorial plus f triple prime at 0 times x to the third all over 3 factorial plus and so on. See if we see the pattern. This is e to the x is equal to, well, f of 0 is 1 plus all the derivatives were 1, so this is just x plus x squared over 2 factorial plus x to the third over 3 factorial plus and so on plus x to the n over n over n factorial plus and so on. This is equal to the summation as n goes from 0 to infinity of x to the n over n factorial. Well, here's the neat thing. Give you a second example. If you have e to the, say, 5x, don't worry about doing the work. This is based on this. You have this, put this in your head, that e to the x is always the summation of x to the n divided by n factorial as n goes from 0 to infinity. So wherever I have x, I'm going to write 5x. This is the summation as n goes from 0 to infinity of 5x to the n all over n factorial. Number 3. Interesting. What about f of x equals cosine x here at c equal to 0? So f of 0 is equal to 1. F prime of x is equal to negative sine x. F double prime at x is equal to negative cosine x. F triple prime of x is equal to sine x. Fourth derivative of x is equal to cosine x. You work till you see the pattern. Fifth derivative, negative sine x. Get just one more. Sixth derivative, evaluated at x, is negative cosine x. So now we plug in x equal to 0. So we have f prime of 0 is equal to 0. F double prime at 0 is negative 1. F triple prime at 0 is equal to 0. The fourth derivative at 0 is 1. The fifth derivative at 0 is 0. The sixth derivative at 0 is negative 1. So if you see the pattern, I think we can build it. So here, cosine x is equal to, that first term we got was 1, right? And then plus 0 times x for f prime minus 1 times x squared for that second derivative divided by 2 factorial plus 0 times x to the third over 3 factorial plus come to the fourth derivative. This is just 1 times x to the fourth over 4 factorial. 5 is 0 plus 0 times x to the fifth over 5 factorial minus 1 times x to the sixth over 6 factorial plus and so on. So you might not be able to see the pattern yet. Let's write it out again. So cosine x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. You see the pattern now. The signs are alternating and we're just picking up even terms. So the next one would be plus x to the 8 over 8 factorial minus x to the 10th over 10 factorial. You get the picture, plus and so on. Plus the series terms are alternating, so it's negative 1 to the n. This is x to an even number. We represent that by 2n. And then the factorials are even as well. So this is 2n factorial. Well, you know it keeps on traveling. So cosine x is equal to the summation as n goes from 0 to infinity, negative 1 to the n times x to the 2n all over 2n factorial. Okay. Now, what about to build the so-called sine function? And here's the neat thing about the cosine. Let me make this number 4. What if you have f of x is equal to cosine of, there's a problem in the book, I think it's 3x. It's probably sine, but it doesn't matter. This is the summation as n goes from 0 to infinity. I take this guy right here, and wherever I have x, I write 3x. So this is negative 1 to the nth times 3x to the 2nth power all over 2n factorial. Once you know something, you can use what you know to get something else. Save you the time, right? Number 5. F of x equals to sine x. Here, c is equal to 0. And I want to show you something, that if we integrate cosine, doesn't that give us sine as well? Show you something over here. So sine x is equal to the integral of cosine x dx. I'm going to integrate the power series. So this is the integral of the summation as n goes from 0 to infinity. Negative 1 to the n times x to the 2n. This is all over 2n factorial dx. So sine x, we integrate. You can write this as the summation of the integral. That's the neat thing, but because this series here is continuous over the terms, so this is written as the summation as n goes from 0 to infinity of the integral of negative 1 to the n times x to the 2n over 2n factorial dx. Now you integrate, this is the summation as n goes from 0 to infinity, negative 1 to the n. This is x to the 2n plus 1 all over 2n plus 1 times 2n factorial. That gives us 2n plus 1 factorial plus some constant c, because this is an indefinite integral in terms of the integral, right? So here, sine x is equal to, the summation is n goes from 0 to infinity, negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. Now let's see if we can get that by just working this out the old-fashioned way. So f of 0 is 0. F prime of x is cosine x. F double prime of x is negative sine x. F triple prime of x, negative cosine x. The fourth derivative at x is negative times negative, so we get sine x. The fifth derivative at x, cosine x. The sixth derivative at x negative sine x. Let's do one more. The seventh derivative at x is negative cosine x. And we evaluate these terms at 0. So f prime at 0 is 1. F double prime at 0 is 0. F triple prime at 0 is negative 1. The fourth derivative evaluated at 0 is 0. The fifth derivative evaluated at 0 is 1. The sixth derivative is 0. The seventh derivative at 0 is negative 1. Notice that the signs with the cosine and sine, they do oscillate. And that's pretty neat. Everywhere you see that. So we say sine x is equal to, there's no approximation now. Now that first term there gave us 0, right? And then it's plus 1 times x for the first derivative plus 0 times x squared minus 1 times x to the third. And, we need to divide by the factorials because that's in the definition. Plus for the fourth one, it's 0 times x to the fourth over 4 factorial. The fifth is plus 1 times x to the fifth over 5 factorial plus 0 times x to the sixth over 6 factorial minus 1 times x to the seventh over 7 factorial, and so on. Let's clean that up. This is sine x is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. See where it's going? So now the next one will be plus odd terms, right? X to the 9 over 9 factorial. I think you get it, plus and so on, plus negative 1 to the n times x. How do we build the odd terms? That's represented by 2n plus 1 over 2n plus 1 factorial. You keep on traveling.